So let's start here. So in our equation, if A it becomes equals to the B, then if you can substitute in that relation, we can get the, if A becomes equals to B and substitute that things here, UGT will be equals to 2A cos kg into e to the power I omega t. Now please understand that this is your displacement equation, and this is your g factor, and this is your time. So that means that's your, as the wave propagate, it has a time. So this is this much. Now, if you when you recollect your physics, when a wave things, so this wave we call it as a standing wave, right? So that is what we call it as a standing wave, because it has a amplitude of this 2 kz, right? Now the question is this, that if I have a the surface is equals to the g is 0 at the surface, g equals to 0, and this is your g equals to your h, right? So if you put the surface at g equals to 0, that means the displacement u, the g value will be equals to 0 and t, and at the depth u is the displacement, the g value equals to h and t. So if you put the here the g 0 in this equation, if you put the g 0, so this is cos 0 equals to 1. So it is a 2a e to the power I omega t, and if you put the g equals to h, then this is the 2a cos kh into e to the power I omega t, right? So if you can cancel 2a and 2a, so only part remaining is 1 by k into h. So k value is the wave number, so that will be equals to omega by vs, right? So it's a omega by vs multiplied by h, right? So cos omega h divided by vs. So amplitude of the wave, if you can see that, so that will be the transfer function. So that, because this is your transfer function f1w, which is a basically the ratio of the displacement at the surface by the displacement at the depth, right? So that value equals to 1 by cos kh, or 1 by cos of omega h by vs. So this is your amplitude of f1 wave, or the amplitude of f1. So that means it is the amplitude of the transfer function, and amplitude of the transfer function equals to 1 by cos omega h by va. So if you can put this relation, so that means on this side it is f1 omega, and on this side this is either omega, it is a kh, okay? If you either put a kh or it is a omega h by v, then you can see that it will have a peak at every pi by 2 interval. So pi by 2, 3 pi by 2, 5 pi by 2, so that means at each odd pi by 2 you will be getting a peak. So from this peak, if you know that this will be equals to the cos of pi by 2, so then from here you can find it out what will be the, if you know the vs, you can find out what will be the depth of the swirl column, right? So this is your predominant frequency, that you can understand that what will be the predominant frequency value, and if you know the predominant frequency value, then you can put it onto this one, And if it is a single layer case, of course, then that thickness of the single layer, you can find it out, right, from the predominant peak values. Make sense or no?
In this case, the peak are same for all waves. So
Yeah, because this is the design part, so this will be all same because this is single layer.
So if you have 2, 3 layers and bigger, then that is according to the layer.
But the predominant period is what we will be looking for. Okay, so the predominant period value we will be looking for, and that predominant period means it's a first fundamental frequency, right? So first fundamental frequency we will be trying to find it out, and then from there we can calculate the things. Okay.
Sir, for finding this transfer function, physically what the like how we find it too? Like what are some position is because as you said, you can find the age, the layer tickets.
Yeah.
But for that we need some checker on.
Basically, how do we do that? So if we have a observation underneath the borehole and a observation underneath on the top of the surface, if you can imagine like that, okay, so then if you can take the ratio of these and calculate, right? So that's the main part, or if you able to find out by this transfer function of the soil layers, then you can definitely pointing out that whatever is the fundamental frequency of this wave. So if there is something, we'll be doing that, Professor Agarwal will do that. We will be calculating the HVSR and all these things. From there we can find out the peak, where is the predominant peak, and from this predominant peak we can find out that what will be the depth and the frequency of this, of that particular fundamental frequency of that particular soil. That is important to know because we cannot build a structure or design a structure whose fundamental frequency is same as the fundamental frequency of the soil underneath, because then that structure will immediately set into the resonance, and then the structure will be gone. Okay, very probability the structure will be gone. So we need to avoid that situation as much as possible. Okay. So same. So earlier things is nothing. No damping was present. Now let us assume that the soil has a damping, right? So this is located again on the rigid bedrock, but let us see it has the soil layer is a damp soil layer. So that means when the wave propagate through that soil layer, it get damped. Okay. So the damped soil layer equation for the Kevin White things we have already got, that is our solution, right? We have already proved that. So that's our solution, and the solution of this equation is I omega t plus k. So this part, it's important, right? So this is your k star, so that means it is a complex number now. Earlier part we have used the actual things because there is no damping, but now it is basically a k star part. Okay. Now this k star is the complex wave number. So that is what we call it as a complex wave number. Okay. So the modification is this, that this will be the same as the previous one. Only thing is this, that there is a damping part, this is a k and this is a minus k, and this is your k value is basically omega h by Vs, right? So that's a pure wave number because there is no damping, but if there is a damping present, we have to include that, and that will be the case part. Okay, so in that way, the excuse me. So then, if F2W, if it is a transfer function, then just like your previous one, only part is this, that this will be k star, right? So that is a cos kh. In the previous case, it is a cos k star p h, because this star means it's a complex, and the k value, if you see the two slides before, I had written that the k prime will be equals to into k into 1 minus I of this damping. So this is the damping. So k star is basically k into 1 minus damping. This is the real value of the k, and this is the k into I part. So that's the imaginary component of the wave number. So if you can do that, then it is a omega h by Vs into k plus I. I have, if you can go few slides back, you can see that equations. Okay. It's taking so much time to go. So here I have all put the different modulus and the different things in terms of your all your k values or the damping values. So here I had shown you all the different k star equals to g by this one, and then put that g star equals to g into 1 plus 2i this one. So put this number here and take it on the upside. So because the k prime is equals to the omega into
Excuse me, sir. Sir, in wave number.
damping. If the things are realistically, if there is a damping and the damping is present for everything, so basically the wave number complex means it is a real part and an imaginary part. Now here this imaginary part comes out for the soil, since it's a damped soil always, because there is a viscous damping is present. So therefore that part is basically contributing to the imaginary component. So that is what I have reduced it here. Whenever there is a viscous material present, if this is the equation, then this is the form, and then the form will be equals to, if you do this part of the put, then this will be g into I omega n. So that part is actually contributing to the imaginary part, and that imaginary part, if it is a solid material, then that thing is not present. But in case of your liquid medium, since the viscous material is present, so therefore the damping side is there, and that is why it's a complex number. Okay, so this complex number is equals to the so this will be the rho by g star. So omega into rho by g star. So rho by g star when equals to g into this one, when 1 plus 2i into damping. So this will be equals to omega into rho by g into the so this is equals to rho by g into 1 plus 2i into damping to the power half. Right, so that then you can make it a g into 1 minus 2i, this one to the power half, and then half will be cancelled. So then this will be equals to omega into root over omega into rho into g, or sorry, rho by g into 1 minus 2I into xi. So this is rho by g, and this will be equals to half, right? So that will be half if you can expand it. So this is 1 minus half, and 2 get cancelled. So this will be again you can express this in a different type of the damping relations, right? So what has happened due to the damping? Oh, zoom this thing. That will do? Okay. So that is your damping part. Let me go back to the. It takes so much time to rotate, move. Don't know why. Cool. So transfer function. So I have tried to, so omega h into this much, omega plus this. So this will be equals to v star. V star means it's a g star by rho. Then again g star means g into 1 plus 2I into zeta by rho. So this was zeta by rho, and this is what I was trying to show you, that this will be equals to v star will be equals to vs into 1 plus 2 prime, right? So v star will be equals to your vs, or the vs into 1 plus 2 igs. So if there is a damping, due to this damping presence, everything becomes the complex things. So k star equals to omega by vs, so this will be k into 1 minus xi. So everything will be expressed, all the parameters will be expressed as a complex parameters, right? So if you calculate the amplitude of it, because this is your Fw equals to this much, so if you can calculate the amplitude of this F1W, this amplitude of F1W will be equals to the, since it's a complex number, so it is the cos square kh plus k xi into h. This will be the whole square. So that means, because we know the cos of x plus iy, cos of x plus iy equals to cos square x plus sine hyperbolic y, right? So if you can see that at a very small value of the y, if y is very small, the sine hyperbolic y is mostly the y square. So therefore cos, this function, the cos square of kh will be equals to the k xi h whole square. So this will be equals to cos square omega h by vs and this number, right? So if damping is very small, so that means this value is very small, so its square value will also be much more smaller. So then we can get it as a 1 by cos omega h by vs, same thing as we have done it before, right? If the damping is small. But if the damping is more, then this value we cannot neglect, and then we have to take care of that number, right? So so therefore the in case of your previous plot, in case of your previous plot, you have seen that these things is going to infinite, right? Because the cos kh, it will be 0, so 1 by 0 it becomes the infinity, right? So this will be the infinite value. But here, since there is there is an additional term is present, so therefore the amplitude of the transfer function will not be infinite, right? So that means the down part or the denominator part will not be 0. Okay, so there will be some number will be present, and therefore the transfer function is a different. Let me see whether I have. Yes. So if you see that as the transfer function, as the damping increases from the 5 to 20, the amplitude all get decreases, right? But this amplitude, even if at the 0 damping, or might be the 5% damping here, 5, 10, and 12. So 5% damping, this value is 12. If it is a 0 damping, it will still be a number, but cannot be 0. Okay, so that's why if it is a damped soil, then the transfer function will not be going to 0, and that is what you mostly observed in case of your any transfer function calculation, that you will be not getting the peak value should not be at infinity. So that has to be pure amplitude. Okay, so that amplitude you can calculate, right? So if you can see these things in a z by h, if you can plot on this side, and this is the displacement or u value, you can see that as the damping becomes 0, the soil is displaced in the horizontal direction, because that's the u direction. So if the wave propagates here, the soil is displaced, and that displacement, or the maximum displacement, if it is a 1, if we assume that with a n equals to 0, then you can understand that as the damping increases, I think this is the damping, or oh no, so this is your this is your the motion. So that means it's a fundamental frequency. So that is n equals to 0. It's a fundamental part. So that is your fundamental movement, and this is your different mode of vibrations, right? So this is the fundamental mode of vibration, and this is the first mode vibration of the soil column, and this is the second mode of vibration of the things, right? So so that we can calculate if you have a damped soil present, right? Now let us assume that a uniform damped soil is present now on an elastic rock, which is most appropriate in the case, in the nature that the rock, whatever we are seeing, that the rock is also elastic material. So elastic material basically means the wave, it passes through this one and then come back, and then it will be also transmitted back to this layer, right? So this is your rock amplitude. Then some part of the rock amplitude goes to the soil, and then it reflects from the soil, and then coming back, it is the reflected values from the rock material, right? So let us assume that this has a modulus of rigidity G soil, and it has a density of rho S, right? And it has a thickness of H, and this has a modulus of rigidity of rock is GR, and the density of the rock is rho R, right? So so this is your elastic medium, so that means the rock will now transmit the wave, unlike the rigid bedrock when the rock was not transmitting anything, right? So we are denoting the S for the soil and the R for the rock, right? So these are the two things we are writing out. So we have seen that if it is in a damped case, the displacement in the soil is equals to the some value AS, because that's the amplitude of it, AS, and to K plus because that is going up, and then BS, that will be going down, so that will be this part of the equation. So AS plus BS, and the URT equals to AR, which is going up on this side, and plus BR into this one, right? So at the free surface, because there is nothing is going out and nothing is coming up, so therefore the AS, whatever this, has to be the BS. So at free surface, AS has to be equals to the BS, because there is nothing can transmit to the air. Okay, so the displacement stress are continuous at the boundary. Both the displacement and the stress equation are continuous at the boundary. So boundary, there is no accumulation of displacement and there is no accumulation of stress, because this is a continuous layer. So therefore no stress and the displacement development at the boundaries. So at the boundaries of the soil, if you say that US at this part, that means at the JS equals to H, and the displacement at the rock, this has to be the same, right? So basically at this point, the soil part JS equals to H means here, and UR means the rock, ZR equals to 0, because that is the rock 0. So rock 0 has to be equals to the same. And similarly, the stress, whatever stress developed at ZS equals to H has to be stress developed at ZR equals to 0. So if you can do this equation, so if you can put your H terms here, because USH, so USH means instead of a ZS, we put the H, so A into A, sorry, because your AS equals to BS at this point, so AS equals to AR plus BR for this one, because all the other term for the AR and BR will be equals to Z 0. So put that Z value 0, so it will be AR plus BR, and but here it will be AS, because AS is already equals to the BS, so we can take common, so this will be like this. And if I take the tau values here, so the tau values will be equals to, so similarly AS equals to BS, so if you can do the tau means it's a basically the differentiation of dUs by dg, so if you can calculate that, then this is another boundary condition for this part. So if you can put that, then AR and BR will be equals to this GSKS by GRKR, so that ratio into AS into this part, right? Now, if you can put this GS by K star and this one, so this one equals to rho S and the V S for the soil surface, because this is Ks, so this is your Vs, that means shear wave velocity at the soil surface, and this is your shear velocity at the rock surface, right? So this is the Vs at the rock surface. So this is Kr will be the shear velocity at the rock surface. So that is a impedance constant, or we can say it's a complex impedance ratio, or it's a complex impedance. Okay, complex impedance, and that we call it as a alpha z. So alpha is not the pure velocity. Alpha is here as a complex impedance ratio, alpha part. So if you can solve these two equations, then your AR will be coming as this one, BR will be coming as this one. Just do a little bit mathematical jugglery. It will be easy to prove. Okay, so so since your AS and A I think okay, so I think this has to be the AR, but anyway, they have put now A here. So this is your AS by AR. So that is the amplitude at the surface, amplitude, and at the rock amplitude. If you can do that, so basically these two get cancelled. So then you can get this number will be equals to this one. So this is your this is basically your transfer function for the soil. Okay, and that will be equals to F3 omega. So this F3 omega, if you can write it down with these things, this will be omega is Vs prime, and then this is equals to I by alpha z, right? So that alpha g is the impedance contrast ratio. So that will be coming into account, right? So if it is if there is no damping present, so that means xi will be equals to 0. If you put that, then this will be equals to cos square kh s n plus alpha square sin square kh, right? And that will be equals to, if you put the F3 this one, so at impedance ratio, if it is a 0.0, impedance ratio means it's basically the alpha z, right? So if it is alpha g is 0.0, then this will be equals to the sin square kh and sin square ksh, and that will be equals to, so that means this will be equals to 0, this part. If the impedance equals to 0, then this will be equals to 0, so it will be 1 by cos square kh. So it will be the same type of graph as we are getting it in the case of first, right? So that's a cosine curve will be the infinite, right? Will be the infinite. But as soon as you have a impedance ratio, then the value decreases substantially, and the amplitude value or the transfer function value is basically substantially decreases, right? So here also you can see that if there is a elastic rock present and there is a damping of the soil, then also it is a possibility that your fundamental value can be 0 depending upon the impedance contrast. So impedance contrast, if it is a 0, so that means rho s Vs prime equals to rho r Vr prime, right? So that will be equals to 0 means that rho s Vs equals to 0, right? So that's a hypothetical case. So therefore, or might be the approximately 0. So then this value will be infinite. Okay. Now, so if we assume now a number of layers, so that means on a elastic rock. So this is an elastic rock, and there are number of soil layers. Okay, so this is your number of soil layers are present. We can say that, and we can have a special layer which is the ith layer and I plus 1th layer, right? So there are two layers, I and I plus 1 layer, and this is a damped, these are all damped soil. And this is our most realistic case, that there is a damped soil, a lot of layers are present, and it is rest on a elastic bedrock, right? So that's the case, and in that case, for each layer, we can calculate the UJT, right? So that UJT, you can calculate for this one, so A into this one and B into this one, and then we can calculate the tau at J into T, and then also the displacement at each boundary, right? And so at J equals to 0, J equals to 0 T, and AN plus BN into this, and this is your M layer, and then G equals to HM will be equals to this much, right? And we can solve this equation by a recurring relation. By a recurring relation, I will not go in details from this, because if you know the M and M plus 1, these two layers you can identify, and then write down the equation for M and M plus 1. So that is what exactly they were doing, A layer and AM plus 1, and this is your AM and BM value. Although the AM is equals to BM, that you can always write it down at the surface, right, at surface. I take it back. A1 is equals to B1, so that means at the surface layer, A1 will be equals to B1, and that you can put it as a recurrence relation. You first find out 1 and 1, when a 1 and 2, then calculate 2 to 3, then 3, 4, 4, 5, and so on and so forth till you hit the elastic rock. So that recurrence relation you can use and calculate your lambda m prime with this one, and then also your transfer function. Now this transfer function, if you can calculate it, it will be something around A1 and B1 with both have a omega, and then AJ and BJ with both have a omega. Now that J can go from any level from 1 to, let's see, the capital N. So that will be the capital A1 to AN part, and AM we can first calculate, will be equals to this one, and substitute the relation 1 by 1, and we can find out all the numbers, right? So this will be the case that there are all the layers, and each one with a U1, this is U2, this is UN, this is UM plus 1, and this is your oxide motions, right? So this is your oxide motions. So we can calculate that by putting the displacement equation and the stress equation, and then write it down with your this relation with your both the part, and you can solve this. So if you can see it here, what we will be doing is this, that we have given the acceleration at the bottom of the layer, and then this is the transfer function for a system of layers, and this is your Fourier amplitude of this data. So this is your Fourier transform of the data, and then this will be the transfer function of this layer, of this 4-layer, whatever is present. So that is your transfer function, and then if you can multiply this Fourier transform with this number with your transfer function, then you got the acceleration at the or the spectral value or the at the top of the boundary, at the top of the layers, right? So that means if you know at this point the time history, then you can find out at this point what will be the Fourier transform if you goes through this one. So you need to calculate therefore this transfer function first. If you know the transfer function, calculate the, so this you will be automatically doing, because that is your inside the borehole or something like that on the rock side. Then you take the Fourier transform of it, and if you know the transfer function, just multiply your rock side Fourier transform, you can get what will be the soil side Fourier transform. And if you know the soil side Fourier transform, I can calculate the inverse Fourier transform to compute the time history at the soil samples, right? So that's the things we have to do, and these entire things can be done in a code. This code is a very famous code for all the geotech engineers they use. It is called SHAKE, S-H-A-K-E. This is your SHAKE code. The SHAKE code will take care. You will be define your rho value and the density value. You have to define for each layer the density and the velocity. Okay, so density and velocity for 1, density and velocity for 2, VS2 and so on, and also the density of the rock and the velocity of the rock. That you have to define, and also the depth of each layer you have to provide, right? So if you give these things, these two things, then what will happen, that if you can give any time series data recorded on some sort of a rock in your area, then you can calculate. So the things will be like this. Say suppose at this site, I said to you that this is your rock site station, right? So this is your rock site station, and this is your soil site station. Okay, so what I did, I take this rock site data here, okay, and then that data we propagate it through the soil column, and if we know each soil part, how much is the motion, so we can calculate from the rho 1, rho V1 or VS1, rho 2 by VS2, if you know that, to say rho 4 by VS4. So this is a 4-layer model, and what you calculate from here, the transfer function of the soil column. So if you know the transfer function of the soil column, then in future, if you give any So this transfer function, if you know, in future, if you like to give any type of motion, then what will be the output at the surface, you can calculate, and then that output you can take the inverse Fourier transform and get a time series data on the surface. Okay, so this is commonly, as I told you last time, that we do the stochastic simulation for creating a earthquake at the bottom of the ground and take this shake program to compute it to the surface, and that will be the surface features at that point, because as you understand from the last class from the stochastic simulation, we have to give the site response values, but the site response value we do not know. So what we do is the site response, we make it as a 1, because the 1 means it's basically the rock things, because the rock will not produce any site response, right? So rock site response is 1. So if you put that site response component in the stochastic simulation as a 1, then you can take that time history, whatever you have generated is for the rock, and put it to the bottom of the site. So if you put it at the bottom of the site, then you use the shake program by defining all the layers from your geotechnical data. You can get the density and velocity data from the geotechnical well logging, and that you can propagate it by the shake program to the surface and compute the transfer function. So if you know the transfer function, then you multiply it with the Fourier transform of the recorded data at the bottom of this one. You can calculate Fourier transform at the surface, right? So if you know the Fourier transform at the surface, then you can calculate the time history at the surface. So that's usually we do in case of any motions.
Can we input MSW data? MSW data, time series data, surface data. As you're saying that we need one time series data, and then it will show the respective time series in the layers.
MSW will be giving you the velocity modeling, right? So that will give you that's a method to calculate the layered velocity of a soil sample. So that's a layered velocity, but that will not give you any response of the soil. So the surface wave MSW is a surface wave analysis, and that will give you if you do the inversion of your dispersion curve, then you can get the layered velocity model, and that layered velocity model is what it is required at this point. So that means you know this one, but I do not want that one. I want that if there is an earthquake happens, then what will be the time series at the surface site. So that is what I wanted, right? So for that, what you need to have a time series to be generated at the bottom or the rock site, and then you propagate it through that soil column whose velocity and density you already got, that you propagate it, and then that will be giving you the Fourier transform spectra. If you multiply, it will give you the transfer function, and that transfer function, if you multiplied with the Fourier transform data of this one, then you can calculate the Fourier transform due to the soil layers. right? And then that Fourier transform, you can convert it into the time domain and you can get the time series data. Does it make sense? So that means these are the things. Now, as I told you that sometimes that there are number of ways you can do that, because the ultimate product we have to have, or engineers have to have, is the time series data of that soil sample where they are trying to construct a high-rise building or might be multi-million-dollar buildings, right? So they need to be careful about. So, but they don't have a seismologist, and they do not know how to generate this stochastic simulation. And most of the cases, this is like that. Most of the cases, this is like that because who will be generating this stochastic seismological data? Because they had not taken the class from me, so they cannot generate that, right? So what is the alternate thing to an engineer who do not know how to stochastically generate the data? So as I told you, if it is possible, they had some sort of a surface data for a very past earthquake, then they can use that because that is available to them, right? If they do not have that, then what they will do, they will take the data from other part of the country where we have some recorded data. Okay, some recorded data that they search and find out some, say suppose 8.9 data from Japan, they got it, right? So that data they bring and put it under the rock site and propagate it through the things. But there is a problem. Now what is the problem? The problem is this, that data, whatever you have bring in, the seismic hazard level of Japan is not same as the seismic hazard level of the site where you are analyzing. So that means their hazard level of recordings are different. So if you put your sensor here and a 8.9 magnitude earthquake took place here and a 8.9 magnitude at the Japan, if you compare it, they will not be identical because their rock, their soil, their everything is different, and you are bringing it here and try to tell them that is the things. Yeah, the engineering, as I told somebody yesterday, that the engineers are always have some sort of a factor safety in their design. So that means although this will be like this, but they always give a little bit more so that in case there is an exceedance of that value, the building still survive. So that is always the case. But we have to therefore do a spectral matching for the spectral level of your site to the spectral level of the Japan site. So we have to either increase the level or decrease the level and make it a spectral matching type of thing, so that it looks like that Japan data also you are using, but your level has been either reduced or increased, so that your site will be conformable to that. So that is called the spectral level matching of the place, and that you have to do from the seismic hazard level of your area, that you have to find it out. Okay, so it is not that you take the data and propagate it. No, it is not like that, because that will be wrong. But if you can stochastically generate, then you can generate with your values of Q values, with your local values of this data. If you have, then you can generate it. That will be easy. But if you do not have that, then you have to take the data from other. Not only one, you can take the few data from that level and try to propagate it through the soil column and try to calculate their PGD and PGD values from this one. Okay.
So, sir, we can then simulate many earthquakes and then take the realization in the end.
Yeah, you can do that, the mini earthquake and this one, or you can take the mini earthquake from different regions, check their spectral level, adjust their spectral level, and then take that spectral level, check data, and then propagate it through the SEC analysis. Then that will be fine. Okay, so so if you are in a organization where they can spend the money, so ask them to purchase the SEC tool. So that SEC or ProSEC. Now they have a better version. It is called ProSEC, and the ProSEC is a the SEC program has been make it a Windows compatible and the user type of user interactive type of things. So then that can be used for your analysis. Earlier SEC program is basically Fortran based, and it was you have to give all the parameters by typing the numbers. But nowadays they have a nice opening front, and you select each and every layer, give the layer type and all these things, and you can compute that. Okay, so that's your that is what you have to do, and then they calculate the function at the top of the soil layers. So that is your one-dimensional analysis, or this is your one-dimensional analysis for the SEC is a basically equivalent linear method. So that means it will be, it can handle a little bit about non-linearity of the soil, but not a tremendous non-linear soil. Then we have to have a non-linear type of SEC analysis, which is also present in the system, but that's a little bit complicated type of things. But the SEC analysis is very easy. Doing we have checked the output obtained by the strata and output obtained by the SEC program. They are same, and this you can download it in your computer, and it is not taking a lot of space in your computer either. So this strata program is also a 1D equivalent linear analysis of the soil column, right? So that you can also use, and I will show you in the next week some class in the tutorial how to use the strata.